This lab deals with the time characteristics of capacitors and inductors. A capacitor is a device for storing charge for later use. The amount of charge stored depends on the capacitance, C, and the applied voltage, V. Charge equals the product of capacitance and voltage, that is, Q equals C times V. Capacitors are useful in defibrillators, stun guns, electronic flashes, cattle prods, radios, computers, and even neurons. When capacitors are connected in series, they all store an identical amount of charge, Q, but have different voltage drops. The equivalent capacitance is found by adding the inverses of the individual capacitors and then inverting the result. When capacitors are connected in parallel, they all have an identical voltage applied, but store different amounts of charge. The equivalent capacitance is just the sum of the individual capacitances. The first part of this lab involves measuring the capacitance of each of two capacitors using a capacitance meter. First, measure the individual capacitances. Here we measure the parallel combination of capacitance. Here we measure the series combination of capacitance. While you have the meter, you can use it as an ohm meter to determine the value of the resistance you'll be using with the capacitors. When a capacitor is connected to a voltage source through a resistor, it does not charge up instantaneously. Here the capacitor is ready to begin charging as soon as the switch S is closed. Upon closing the switch, the capacitor charges rapidly at first, then eventually approaches its carrying capacity, Q equals C times V. The function that describes the growth of charge as a function of time is called an inverse exponential. Q equals Q max times 1 minus e to the minus t over RC, where e is the base of the natural logarithm. Although in theory the capacitor never fully charges, in practice it is about 2/3 charged after one time constant given by the product of R and C. A large value of resistance will slow the rate of growth, and a large capacitor will take a long time to charge. A fully charged capacitor also requires time to discharge. Here is a capacitor ready to drain through the resistor once the switch is closed. After the switch has closed, the charge quickly moves from the positive side to the negative side to neutralize the charges in the capacitor. Eventually the current slows to a trickle as the capacitor is depleted of charge. The function describing the discharge of the capacitor with time is a decaying exponential function. Q equals Q max times e to the minus t over RC, where once again the characteristic time for the discharge is the RC time constant. In practice, it is possible to use a special switch to flip easily from a charging capacitor to a discharging capacitor. In this position, the switch allows the capacitor to charge. Thrown to this position, the switch allows the capacitor to discharge through the resistor. For circuit assembly, connect the positive pole of the voltage source to one side of the switch. Connect the center of the switch to the resistor. Connect the capacitor in series with the resistor, and complete the circuit to the negative pole of the voltage source. The other side of the switch is connected to the low voltage side of the capacitor. Voltage sensor leads from Science Workshop will monitor the voltage across the capacitor. This is the same as measuring the charge, since the two are proportional to each other. Toggling the switch will either charge or discharge the capacitor. Here is a plot of the voltage across the capacitor during the charging process. And here is the voltage as the capacitor is discharged. If we fit an inverse exponential to the charging capacitor data, we can determine the RC time constant. Fitting a natural exponential function to the discharging capacitor yields the same RC time constant. An inductor is a device that opposes changes in the current flowing in a circuit. If a circuit initially has no current flowing, the inductor will oppose the buildup of current. If the circuit already has a large current, the inductor will oppose the reduction of that current. In this circuit, the voltage supply is prepared to cause a current to flow as soon as the switch is closed. The presence of the inductor in the circuit opposes the increase in current such that the current builds up according to an inverse exponential curve. Now the time constant depends on the quotient of the inductance to the resistance. The larger the inductance, the longer it takes for the current to become established. If the inductor already has current flowing and the power supply is removed by flipping a switch, the current decays away at a rate that once again depends on the ratio of L to R. Begin by measuring the inductance of the coil L using the inductance meter. Then use the meter as an ohm meter to measure the total resistance of the coil and 10 ohm resistor combination. This is the total resistance in the RL circuit and should be used to calculate the time constant. Because the time constant for this small coil is short, you cannot keep up with a mechanical switch. Use the internal power supply set for square wave mode to flip the circuit on and off. Though we cannot measure the current directly, we can monitor the voltage across the resistor and know by Ohm's law that the current will be proportional. The current in the circuit appears as a square wave, toggling on and off. But a close examination of the leading edge, zooming in, shows that the inductor slows the rate of change of the current. By fitting an inverse exponential function, you can determine the time constant, L over R. Close inspection of one of the dropping edges shows that the current decays as a natural exponential curve. Again, we can get the time constant.